Hi everyone, in this second example we will look at the Wallen High School by Calatrava. It's an assembly hall, 16 meters by 20, and it's covered by five prefabricated 3-pins arches spanning 8 meters. So there are two sets of arches, 5 lower arches which have an elliptical shape, and 5 upper arches which have a parabolic shape. So in terms of convention, we will define all the work with the axis of these arches, and we will call the crown the highest point and springs the lowest point, and the span is the distance between the two springs. So in terms of workflow, we can start defining a point for each arc on the XY plane. We can then rise these points in order to create the crown and the springers on both sides. And we can then draw the arches and divide them to form the vertical diagonal struts and the top horizontal struts. We will then see how we can import this geometry into Revit. So in terms of inputs, we will need to define the number of arches, the distance between them, the height both of the crown and the spring, the span, and the number of vertical and horizontal struts. So let's start with Dynamo. Let's save this, calling work in progress. We can start with two inputs, which are the longitudinal length of the space and the number of arches. So these are two numbers, and we can use the slider. So if we go to core input, so the longitudinal length, we can use a number slider because it could be it could have some decimals. We are setting it to be 20 meters, and the number of arches is definitely an integer, and we will set this number to 11, so 5 lower arches and 6 higher. So in order to create our points, we can first of all create a sequence between 0, which will be the first point, till the length, and divide this distance in the number of arches. So the sequence that goes from 0 to 20, and it has 11 items. We can then create a point Autodesk point by coordinates, and we want to have our arches align with the x direction, x-axis. So we can set the y and the z to 0, and these are our points. We can then define the crown points. So again, we will have two number sliders, the height of the upper arc is 8.2 meters, and the height of the lower arc is 7.5. So if we then want to move every second point by this amount and the rest of the other points by this amount. So we can put these two numbers together into a list, call it h1, h2, and then we can cycle this list based on the number of arches divided by 2. And we will get 12 items. But this, when we take geometry translate, if we leave the lacing set to shortest and we are feeding 11 points, Dynamo automatically will get rid of the latest point in this sequence. So this is what we have. And we can group this point and call them crown points. And turn off the preview of the other point. Okay, so now we need to define the springs point. So we can take the sequence that we have defined before. We can remove and use the same inputs. And in here we set the half width of the upper arc to 8 meters. In here we set the half width of the lower arc to 5.325. And we can call these two W1 and W2. So this is only half, so this is just a translation in one direction. We need to have same list as a negative. So we can use a code block to create this list and the same list with negative values. And then we can use our list transpose node to combine together the positive and the negative translation. The last information that we need is the height of the springs, which again the spring of the upper arc is 6.26 meters, and the height of the spring of the lower arc is 2.85. Now we could use the same set of nodes that we have seen before, but we can also do something else. So we can use a node which is called list of repeated item, and we can repeat the spring height for the upper arc 6 times and spring lower arc 5 times. And then we can use the add item to front to combine these two lists. So we have first item is the higher arc, upper arc. So this is the, and we need to set the lacing to longest. So we have taken first item and the first item and added them together in the same list. Now we can flatten these values to match the number of items that we have in the other list. And we can finally again use geometry translate, taking our base points, giving them a Y translation and a Z translation. So this is how it looks like. Then, in order to draw our arcs, our geometry through these points, we need to have them in the same list and in the same order. So that this point is the starting point, this point is the middle point, and this point is the last point in the list. So we can use a node called insert list insert, and we can use, this is the element that we want to insert, this is the list, and the position is going to be 1. Again, set the lacing to longest, and if we turn off these points, turn off these points, now we have combined all the points in something that we can use. If we try to use the arc by 3 points, and for example we take 0, 0, 0, 1, 0, 2, the first 3 points, we can see that this node create an arc based on the equation of a circle, and it's more evident if we look at the first. See, if we go back to the image, they don't look like a half circle, they are more like a ellipse or a parabola, to simplify this. So Dynamo is quite powerful, and design script is the geometry engine behind it is even more powerful because it allows you to define a function in a code block and evaluate that function by a list of inputs. So we know that the vertex equation of a parabola assumes this formula and visualize the shape, and we know that our vertex is gonna be at what, 8.2 and 0, and the parabola will look down and it will have some, it's not this narrow, it's gonna be something like this. So if we take this equation and we write it into a code block, we can find the value of a based on the 2 points that we know the parabola will pass by. So one is the vertex coordinates and the other one is the spring point coordinate. We can then again rewrite the equation in the vertex format, and if we feed these values and a list of number for x, you can see that this is the list of points that satisfy that equation. And if we do the same exercise for the lower arc, it's even more evident that the shape is completely different. So we cannot use the arc by 3 points. Luckily, we can use NURBS by point because NURBS can approximate or can represent conic geometries very accurately. So if we plug into the points and we set the degree to 2, you can appreciate that the NURBS goes through almost all the points. So we don't need these equations, and we can simply use NURBS. Okay, so the next step is to create the members that are spanning through these arches. So to do that, we can use a point by parameter, point at parameter node, and again the parameterization of the NURBS of curve is usually from 0 to 1, and we can say that we want 38 members and set the lacing to cross products, so we can divide each NURBS into 38 points. We can then transpose these points and connect them using a polycurve by points. so that we have all the vertical struts, and each list or each polycurve is connecting these points. Okay, so we can do the same for the top members, horizontal members. So let's say that they are less than 38. We can set them to 22. We can then again transpose. And the difference, though, is that we just want to connect the highest point, not the lowest. So we can drop items or drop every nth item. So if we drop every second item from each list, so lacing set to longest, and we create another polycurve. Now we have the top lines. Okay, so what we can do now is to create a poly surface. So we can do a loft with these cross sections, and which will represent the underside of our roof. And we can import this into Revit. I think one way is to use a direct shape. The problem with the direct shape is quite powerful because you can assign a category and a material to it. So it's better than importing a symbol or an SAT. The problem with the out-of-the-box category, we can use generic model. The problem with the out-of-the-box node is that when you run it, when you Revit or Dynamo create a mesh and then places the mesh into Revit. If instead we use Spring Node direct shape by geometry, which is exactly the same, we need to we are forced to assign a name. Otherwise, if we try to run, the node will not give you anything. See how much better looks like. So I think could be quite handy to you to have Spring's node package installed and to use that. So finally, we can look at how we can create beams in Revit. So the only difference, the only thing that we need to consider is that the beam by curve does not work with polycurves. So if we try to run Revit, well, Dynamo gives you this error. So before using the curves, we just need to explode polycurves into single curves. And so we run. There is also another catch. So at the moment, the polycurves have been drawn following this alignment, but it would be better to group our beams per surface. So before creating the element in Revit, it's still useful to once again transpose so that now all these beams will be in the same list. And here are the beams. So one thing that you can notice is that Revit or Dynamo has placed the beam quite randomly, apparently randomly, or definitely not following the surface at all. So we can find a way of rotating the beams automatically. And to do that, we need to think at how the beams vectors, normal vector, beam direction, and the vertical vectors are defined. So in order to find the vertical vector and the angle between this vector and the surface normal, which will then we will need to use to rotate the section, we need to first of all find this green vector, which is the cross product between the curve normal and the line direction. So we need to define where we want to perform the analysis or where we want to find the vector. In this case, we could take the center point of the beams. So we can calculate the curve normal at parameter with one node very easily. And the parameter in this case will be 0.5, so the midpoint of the beam. We then need to find the direction of curve. So If we try to use the line direction with a curve, we will get an error. So what we can do is write a function in a code block that converts or casts curve to a line. So it will accept curve and it will take curve dot point at parameter 0 for start point, point 1 for the end point, and will return a line by start and end point, point 1 and point 2. So if we now try this cast curve to line which our, let's call them beams, we have now a list of lines which are exactly the same start point, end point, but in addition they also have a direction, which you can see. So now if we run, this node will work. So we can just take the cross product, and we need to calculate the cross product between the curve direction and the curve normal. Then the other information that we need is the surface normal at point, and the point is going to be the midpoint of our beams. So point at parameter, again these are the curves, parameter is still 0.5, and in terms of surface we need to extract the surface from the poly surface, and having them transposed the beams helps now, because the surface that we are extracting have been generated in this direction. So this is the normal point, this is the cross vector. We can then find the vector angle, and we should use the angle about axis because we want to calculate the rotation from the line direction. So we want to rotate this vector to the surface, and we want to rotate it using the beam direction as an axis. So if we connect the vector cross and the line direction, we get a list of angles. Now we can use set parameter by name. Beams our elements. The parameter that we want to set is cross-section rotation. And the value are these ones. So now we can see that the beams have been rotated and they are perpendicular in this point. So here are slightly out. If you want, you can change where you're performing, where you're calculating the normal. So if you want to use the start point, and this is the start point, this is the end point. So if we do 1, now the beams are aligned perpendicular to this point. And now, as you can see, they are sticking out a bit from the surface.